All right, chi-square test for independence. Probably the more useful of the two tests. Chi-square test for independence. Test whether the distribution of a categorical variable is related to scores on another categorical variable. For example, is criminal sentencing related to ethnicity? Is support for abortion rights related to gender? The example that we're going to look at comes from a study that examined responses to telephone inquiries for availability of apartment rentals. Back in the 90s, we didn't have Craigslist or anything like that. So people actually had to look in something called a newspaper. I know some of you probably haven't heard of those. Something called a newspaper had a section called the classifieds, where you would see listings for rentals. Generally, people would have to place an ad, and it would run for 2 weeks. So, you'd have to call and see if the rental was still available. It's not like it just disappeared when it had been filled. So what this research study did is they called 160 rental listings, and the callers either indicated that they were HIV positive, somehow that came up in the conversation, or they didn't say mention HIV status at all. What the researchers here were interested in is whether indicating HIV status would cause housing discrimination. Amazing that it would. It's not like you're going to catch HIV from renting an apartment to somebody, but want to see if that's the case. Their measure of rental inquiry was the response to the rental inquiry, simply whether the landlord said that the apartment was available or no longer available. The question that they're asking is whether the response to the inquiry is independent of the stated HIV status, or did HIV status impact willingness to rent? Here's what the response pattern looks like. You can see that there's kind of a striking difference already. The null hypothesis, simply rental availability is independent of HIV status, nothing numeric to put there. This is often called a contingency table, which is why this is sometimes called a contingency chi-square. As before, we're going to compare observed and expected frequencies. These are the study results, of course, are the observed. However, getting the expected frequencies is a little bit more complicated, a wee bit more complicated, not that much more. So the observed and the expected frequencies. Well, one way we can do this is we can say, okay, overall, what did we get? Well, we got 58 total positive responses, or 58.1% total positive responses, 41.9% negative responses. If these two things are independent, we would expect that to be the distribution, 58% versus 41.9%. We would expect that to be the distribution regardless of HIV status. So both groups would be expected to have that same overall distribution. So take, for each group, 58.1% of the 80 expected positive responses, 41.9% of the 80 expected negative responses, and there you go. You'll have the values. These don't have to be whole numbers. So you can see it would be 46.5 and 33.5 as the expectation, and that's the same expectation for each group. That's what it would look like if it was independent. How far that is from what we actually observed, and we can see that it looks like there's going to be some pretty big numbers getting squared here. How far that is from what we observe is going to be it's going to drive the chi-square value. Now there's another way you'll see this. It's a little more mechanical. What we're going to do is multiply each row total by the column total, and then divide by the total number. So you can see for the first one, the row totals to 80, the column totals to 93. We divide that by 160, we get 46.5. Similarly, for the next one on the top, row total is 80, but the column total this time is 67. So we multiply those together, divide by 160. Two ways to get to the exact same point, exact same place. I like the other procedure because it's conceptually more in tune with what we're doing, whereas this is just a mathematical shortcut. All right, so the calculations here. Again, really straightforward calculations, not really much complexity involved. Simply for each of these cells, we're going to take the observed minus the expected, square it, and then divided by the expected. We do this and it comes out to 21.6. Where does 21.6 fall in terms of being able to reject the null hypothesis or not? Well, we got to get our degrees of freedom. There's only 2 categories for each of these, so it's just going to be 2 minus 1 times 2 minus 1. And if we go to our chi-square table, the comparison value, if we were using that approach, would be 3.84. We were clearly way above 3.84, so we're going to be able to reject the null hypothesis. What does that mean in plain English? Well, if we look at our distribution, we can say clearly mentioning a HIV status certainly did affect whether people were told the rentals were available or not. The majority of the people who mentioned HIV status got told no. All right, in terms of the R output, you can see some of the code here. First, we need to make a table. First, we can get the proportions. Here, this will give us the different proportional values. Nice piece of information to have. And you can see even more clearly when we look at the proportions, 60% of the people who said that they had HIV were told no, whereas only about 20-some% of the people who didn't mention HIV said no. Chi-square test there, very, very low probability, well below the 0.05 level, tells us that, that ain't a coincidence. There's something about what they're telling the landlords that is affecting their status. Briefly to mention effect size for chi-square, phi, also known as Kramer's V or sometimes W. It's the effect size for chi-square, and one thing you can see is that in terms of its size, it's on the same metric as a correlation. It's scaled to be like a correlation, largely because you got Pearson involved in this. To get the effect size, we need, again, the LSR package. And then we just simply run the Kramer's V command on the object that holds our analysis. So, again, relatively easy to get this in R.